deep inside the sun, below every visible feature, below the storms and the light and the slow roll of heat toward the surface, there is a place that has been burning for nearly 5 billion years without interruption and without rest. It is not a fire in any ordinary sense. No flame reaches this far inward. What burns here is matter itself. Rearranged at the most fundamental scale, the physical world allows four small things pressed so tightly together that they become one slightly smaller thing, and the difference between what went in and what came out moves outward as light and heat and something even stranger than light. The sphere in which this happens extends roughly 170,000 kilometers from the center in every direction. 170,000 kilometers is more than 13 times the diameter of the Earth. And yet within the Sun's vast body, this core occupies only the innermost quarter of its total radius, a fist-sized fraction of something whose full width would swallow the distance from the Earth to the Moon and still have room. The first thing to understand about this place is that it is not solid. It does not behave the way the word core might suggest. The hard center of a fruit, the iron heart of a planet. The material here flows. It moves the way a gas moves, or more precisely, the way a plasma moves, which is to say, it is a gas in which every atom has been so thoroughly stripped of its electrons by the surrounding heat that what remains is a dense electrically charged fluid of bare nuclei and free electrons pressing against one another in every direction at once. It is a fluid. It moves. And yet the density of this fluid is roughly 150,000 kilograms per cubic meter, about 150 times denser than liquid water, denser than any solid found naturally on Earth. A volume no larger than a coffee cup filled with the material at the solar core would weigh as much as a loaded freight car. This is what plasma does at 15 million Kelvin under pressures that exceed anything on the surface of any planet in this solar system by many orders of magnitude. It becomes something for which ordinary language has almost no words, neither liquid nor solid, neither gas nor anything simple, just matter pressed to the edge of its own nature, still flowing, still moving, utterly unlike anything that exists in the open world. The pressure at the center of the sun is approximately 2.5 times 10 to the 16th pascals. That number does not mean much without a reference. At sea level on Earth, the air presses down at roughly 100,000 pascals. The pressure inside a fully inflated car tire is about twice that. Deep inside the ocean, at the greatest depths, the water presses inward at roughly 100 million pascals. The center of the sun presses inward at 2.5 trillion times harder than the air at sea level. The central density of the core, combined with the weight of everything above it, the entire remaining volume of a star, nearly 1,400,000 kilometers across, produces a squeeze for which no engineering analogy exists. And it is precisely this pressure, working alongside the temperature, that makes the nuclear reactions possible at all. Without it, the protons that fuel the sun's fusion would simply drift. With it, they are forced close enough together for something remarkable to happen. Protons are positively charged, and like charges repel. Two protons brought near each other feel a growing electromagnetic push that resists their approach, and the closer they come, the stronger that push becomes. To fuse, they must be brought so close together that another force, the strong nuclear force, can take over. The strong nuclear force acts only across distances smaller than an atomic nucleus. At those distances, it is powerful enough to bind protons and neutrons together, regardless of their charge. But reaching those distances against the electromagnetic repulsion requires enormous speed, and enormous speed in a plasma means enormous temperature. At 15 million Kelvin, the protons in the solar core are moving fast enough, and the pressure is high enough that some among the vast number colliding at any moment tunnel through the electromagnetic barrier by a process that has no classical explanation. Even at these temperatures, classical physics would say fusion should not occur. The protons should still be moving too slowly. The barrier should still be too high. But quantum mechanics allows particles to be found, with some probability, on the other side of a barrier they could not classically cross. The sun relies on this. Without quantum tunneling, the solar core would be dark. When two protons do collide and tunnel through the barrier, one of them converts its charge, it becomes a neutron, and the pair bind together into a nucleus containing one proton and one neutron. This is deuterium, a form of hydrogen. In the conversion, a positron and a neutrino are released, and a small amount of energy is freed. The positron quickly meets an electron, and both are annihilated, producing two gamma-ray photons. That deuterium nucleus then meets another free proton and fuses with it, forming a nucleus with two protons and one neutron, helium-3. Two helium-3 nuclei then meet and fuse, releasing two free protons and forming a single helium-4 nucleus, the stable end product. This chain of reactions, 3 steps, from hydrogen to helium, is the proton-proton chain, and it is the primary source of the sun's energy. Each full cycle converts approximately 4 hydrogen nuclei into one helium-4 nucleus. The helium nucleus is very slightly less massive than the 4 protons that went into making it. The difference is small, less than 1% of the original mass. Specifically, about 0.7% of the mass is missing when the products are weighed against the inputs. That missing mass has become energy, according to the relation Einstein described. Each cycle releases roughly 26.5 million electron volts of energy. In the language of a single reaction, that is an inconceivably small amount. In the language of the full solar core, running these reactions at a rate sufficient to sustain the sun's output, it amounts to the conversion of around 4 million metric tons of mass into energy every second. Every second, without pause, the sun becomes slightly less massive and slightly more luminous than it was before, and the energy of that conversion begins its long, slow movement outward through the layers above. The total power output of the sun, its luminosity, is approximately 383 trillion watts. Written as a number with all its digits, it fills a line. Held as a felt thing, it is the energy reaching every planet, every moon, every grain of dust in the solar system, and still the sun radiates almost all of it into the empty dark in every other direction as well. Photons carry this energy outward, but the production of those photons, the generation of that power, happens almost entirely within the innermost quarter of the solar radius, the core, and within the core, the power is not generated uniformly, but is concentrated closest to the center, where temperature and pressure are highest. Spread across the entire volume of the core, the average power generation is approximately 276 watts per cubic meter. That number is worth sitting with for a moment. 276 watts per cubic meter. A resting human body generates roughly 1,000 watts per cubic meter of body volume, slightly more heat per unit volume than the solar core produces. The sun's extraordinary power comes not from intense local energy generation, but from the sheer, almost incomprehensible scale at which those modest local rates are summed. There are trillions upon trillions of cubic meters of core, and each one producing a few hundred watts, quietly, steadily, without any single dramatic event. The total arrives at something that lights a solar system simply by adding up increments that would feel, to any 1 cubic meter of the core, unremarkable. The core, then, is patient. It has been fusing hydrogen for nearly 5 billion years and has enough hydrogen left to continue for roughly another 5 billion. The rate of fusion is essentially self-regulating. If the core contracted slightly, it would grow hotter and denser, and the fusion rate would rise, producing more energy, which would push the surrounding material outward, expanding the core back toward equilibrium. If it expanded slightly, it would cool, fusion would slow, gravity would pull the material inward again, compressing and heating it. The sun breathes in this way on timescales far longer than any human lifespan, maintaining a balance between the inward pull of its own gravity and the outward pressure of the energy it produces. This balance is called hydrostatic equilibrium. It is not a truce struck at one moment and then held by will. It is a continuous dynamic negotiation, pressure and gravity testing each other at every depth, every moment, throughout the entire body of the star. The core that produces these reactions is not quiet in any ordinary sense. The plasma within it moves constantly, pressure waves propagating through the dense fluid at speeds that dwarf anything familiar. Temperature variations and density variations ripple through the material, the way sound moves through a metal, faster than sound in air, faster than most things that can be imagined moving. And yet at the scale of the core as a whole, things proceed with a steadiness that is almost impossible to relate to ordinary experience. The reactions do not explode. There is no detonation, no runaway, no cascading acceleration. The fusion rate is controlled by the temperature, and the temperature is controlled by the pressure, and the pressure is controlled by the gravity, and the gravity is produced by the mass, a chain of mutual regulation so deeply nested that the system has been running continuously since before the Earth existed, before the continents formed, before the oceans filled, before the first cell divided in the shallows of a young warm sea. Whatever was alive on Earth 5 billion years ago was warmed by the same quiet reactions proceeding in this same core, at roughly this same rate, in this same slow and steady way. The core material, at 150,000 kilograms per cubic meter, is not merely dense in the abstract. It is denser than osmium, the densest natural element on Earth, denser than iridium, denser than platinum, denser than anything mined or refined or manufactured at ordinary pressures. And yet it flows. This is the fact that the mind returns to without quite being able to settle. The material is denser than a cube of solid platinum, the same size, and it flows past itself the way warm water flows, the way breath moves in and out of the lungs. The difference is temperature and ionization. At 15 million Kelvin, the electrons have been stripped entirely from their nuclei, and the mixture of bare protons and bare electrons behaves not as a collection of individual atoms jostling in solid contact, but as a single continuous fluid, compressible and flowing, obeying the laws of fluid dynamics and plasma physics rather than the laws that govern rigid materials. The density is extraordinary. The behavior is that of a gas. Both things are true at once, and neither cancels the other. Pressure at 15 million Kelvin presses equally in every direction. There is no up or down inside the core in any meaningful sense, or rather, every direction from the very center is up, because every direction leads away from the point of maximum compression. The plasma at the exact center is the most compressed material in the solar system. It is compressed by the weight of everything above it, a column of plasma stretching all the way to the visible surface of the sun, some 696,000 kilometers overhead. That column is not static, it shifts. Plasma moves through the layers above, convecting and swirling in the outer regions, and those movements send pressure waves back down through the radiative layers, through the tachocline, into the outer edges of the core. The core is not isolated from the rest of the sun. It sits at the bottom of a structure that communicates pressure and motion through its entire depth. The temperature at the center of the core, 15.7 million Kelvin, corresponds to photons of remarkable energy. The light produced within the core is not the soft visible light that reaches the Earth. It is primarily X-ray radiation, gamma rays, high-energy photons born from the annihilation of positrons and electrons from the rapid deceleration of charged particles in the dense plasma. These photons do not travel far. In the dense plasma of the core, a photon moves on average about 1 centimeter before it is absorbed by an electron or an ion. 1 centimeter. Then it is re-emitted in a new and random direction, then absorbed again after another centimeter or less. This process, absorption, re-emission, new direction, is the beginning of a journey that will take the energy of those original fusion reactions hundreds of thousands of years to complete. But that journey, the long drift outward through the layers above, belongs to the story of what lies beyond the core boundary. At the core itself, the photons are still being born, still being swallowed and remade, still trapped inside the densest material in the solar system, circling in random paths that carry them no meaningful distance from the place where they were made. The energy is here. It has not left. It will not leave quickly. There is a second kind of particle produced in the proton-proton chain that behaves in a completely different way. During the first step of the reaction, when one proton converts to a neutron and a positron, a neutrino is also released. Neutrinos are among the smallest things the physical world contains. They carry no charge. They have only an almost vanishingly small mass, so small that for decades physicists assumed they had no mass at all. They interact with matter through only the weak nuclear force, which means they pass through ordinary matter as if it barely existed. A neutrino produced in the solar core at this moment will take roughly 2 seconds to reach the surface of the sun, crossing hundreds of thousands of kilometers of dense plasma, as though that plasma were not there. A photon born in the same instant, at the same location, will take hundreds of thousands of years to make the same crossing. The neutrino and the photon are both children of the same reaction, born in the same core, in the same moment, and the contrast between their journeys is one of the most arresting asymmetries in physics. The sun produces approximately 2 times 10 to the 38th neutrinos per second. That is a 2, followed by 38 zeros. Every second, they stream outward in every direction, passing through the entire body of the sun in 2 seconds, then spreading into space. 8 minutes after they leave the sun's surface, they reach the Earth. They do not stop there. They pass through the Earth, through the entire rocky iron-cored bulk of the planet, without slowing, without scattering, without registering that a planet was in the way at all. Trillions of them pass through every square centimeter of the Earth's surface every second, including through anyone standing on it, including through the ground beneath them, and emerge on the other side unchanged. They are not dangerous. They are simply indifferent to matter in a way that matter is not indifferent to anything else. They carry information about the reactions happening in the solar core at this exact moment, not delayed by thousands of years the way the sun's light is, not filtered through the layers of the sun's atmosphere, but fresh, direct, instantaneous in human terms, a live signal from the innermost engine of the star. For decades, the number of solar neutrinos detected on Earth was lower than the standard solar model predicted. The detectors built to catch them, vast tanks of chlorine solution buried deep underground, or heavy water chambers beneath the Canadian Shield, consistently registered fewer arrivals than theory required. This was the solar neutrino problem, and it was a genuine puzzle. Either the standard model of the sun's interior was wrong, or something was happening to the neutrinos between the core and the detectors on Earth. The answer, confirmed by the Sudbury Neutrino Observatory in the early years of this century, was the neutrinos themselves. Neutrinos come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The fusion reactions in the solar core produce only electron neutrinos. But as those neutrinos travel from the core to the Earth, they oscillate between flavors, converting from electron neutrinos to muon or tau neutrinos, and back again in a slow quantum mechanical cycling. The earlier detectors were sensitive only to electron neutrinos, and so they caught only a fraction of the true total. The Sudbury detector was sensitive to all three flavors, and when it counted all of them together, the total matched the model exactly. The solar neutrino problem dissolved. The standard solar model was confirmed. The sun was doing exactly what theory had always said it was doing. The mystery had been in the particle, not in the star. The resolution of that problem was more than a technical footnote. It confirmed that neutrinos have mass. They must to oscillate between states, as quantum mechanics requires, and it placed the standard solar model on firmer ground than it had ever stood on before. What the detectors were measuring was the core of the sun, directly, in real time, not its surface temperature, not its spectral lines, not the light it emitted hundreds of thousands of years ago. The neutrino signal was immediate. The fusion reactions responsible for it were happening at the moment the signal was recorded. For the first time in the history of astronomy, humans had looked through the entire body of the sun and seen what was happening at its center, without any of the layers above contributing noise or delay or distortion. The core was confirmed to be precisely as the model described, a sphere of plasma, 15 million Kelvin at the center, fusing hydrogen to helium, quietly producing the energy that has warmed every living thing on Earth since life began. The scale of what takes place inside the solar core is not easy to hold in the mind all at once. It helps to step through it slowly. The core is roughly 340,000 kilometers in diameter, nearly as wide from side to side as the distance from the Earth to the Moon. Within that sphere, the temperature at the center is 15.7 million Kelvin. The pressure at the center is 2.5 times 10 to the 16th pascals. The density at the center is approximately 150,000 kilograms per cubic meter. The total power produced within the core is enough to light every city, power every machine, and warm every living body on Earth many billions of times over, and still have almost all of it left over to pour into empty space. And the mechanism producing all of this, the proton-proton chain, involves 4 particles, each smaller than a femtometer, colliding in a space so small that it cannot be seen, letting the strong nuclear force bind 3 steps of their collision into a new and lighter thing, and releasing the remainder of their mass as light and heat and neutrinos. There is nothing larger behind it. There is no deeper engine. This is the bottom of the sun. The reactions do not happen all at once in some central furnace at a single point. They happen distributed throughout the core, at every depth within it, at every point in the three-dimensional volume of that 340,000 kilometer sphere, all simultaneously, at a rate that is everywhere and always modest, 276 watts per cubic meter here, 276 watts per cubic meter there, and there, and there, and the sum of all those modest, patient increments is the light by which the earth has always known the day. The sun does not burn brightly because anything in it is dramatic. It burns steadily because everything in it is vast. A cup of the core material, if it could be removed and placed somewhere on Earth without disturbing its temperature or pressure, would immediately expand into something enormous and explosive. The pressure and temperature that hold it in its compressed plasma state are only maintained by the weight of the surrounding star. Outside that weight, it would expand and cool. The material is not stable in isolation. It is stable only in context, only because everything above it is pressing down, and the energy it generates is pressing back. Remove either side of that balance, and the object ceases to be a stellar core and becomes something else entirely. This is what the sun is, not a single stable material in a stable container, but a continuous dynamic balance, maintained only by the ongoing transaction between gravity and fusion, between compression and release, between the inward pull of 150,000 kilograms per cubic meter pressing from above, and the outward surge of energy rising from the reactions below. Both sides of this negotiation have been running without interruption for approximately 4.5 billion years. The core is at the bottom of the sun in the sense that it is the innermost region, but it is not at the bottom of the sun in the sense of being passive or inert, or simply something that things rest upon. It is the source. Everything above it, the layers of plasma through which the energy will slowly rise, the convection cells that will churn it toward the surface, the photosphere from which it will finally escape as light, the chromosphere and corona through which it will pour into space. All of it exists because the core exists, because the reactions are running, because 4 hydrogen nuclei are somewhere in this sphere right now, pressing through the quantum barrier and binding into helium and releasing the difference as energy. Stop the core and the sun would go dark in hundreds of thousands of years, slowly, as the last of the light generated by past reactions finished its long outward crawl through the radiative layers, and then finally dark, the outer layers cooling and collapsing inward with nothing left to push them away. The core is not just at the center of the sun. It is the reason the sun is the sun. At the very center, where the pressure and temperature are highest and the fusion rate is greatest, there is no single reaction happening. There is a continuous statistical event, a distribution of proton velocities, a distribution of collision energies, a distribution of quantum tunneling probabilities, and across all of those distributions, at every moment, some number of collisions succeed, while the vast majority do not. The proton-proton chain is not efficient in the way machines are efficient. It is statistical in the way weather is statistical. A small fraction of all possible events taking place while the rest do not, and the aggregate of those rare successes summing to something vast. Most protons in the solar core will not fuse today. Most will drift through the plasma, colliding elastically, exchanging energy, waiting. A proton at the center of the sun has an average lifetime before fusing of approximately 9 billion years, longer than the current age of the solar system. The sun's power comes not from speed or intensity, but from the sheer number of protons available to take the slow chance. The neutrino is the particle that leaves this place fastest. Born in the first step of the proton-proton chain, released from the core at approximately the speed of light, it crosses the entire interior of the sun in roughly 2 seconds and continues outward through the corona, through the inner solar system, through the Earth, through whatever lies beyond, without stopping, without slowing, without acknowledging any of the matter it passes through as anything more than the thinnest of veils. The neutrino does not experience the sun's layers. It does not know the radiative zone, or the convection, or the photosphere, or the corona. It simply leaves. It is the most direct thing the core produces, a particle carrying the signal of a reaction that happened in the deepest, densest, hottest place in the solar system, passing through all of it in 2 seconds as though none of it were there, and continuing outward into the dark of space, where it will travel, unchanged and unimpeded, for as long as time persists, carrying the record of a single proton's conversion in the core of a star that will not remember it. The fusion reactions continue, the plasma flows, the pressure holds, somewhere in the interior of this vast, patient, flowing sphere, at temperatures too high and depths too sealed to ever be visited. 4 protons are pressing toward each other right now, through the quantum dark, and the result of their meeting will become in hundreds of thousands of years the light of an afternoon. The core does not hurry. It does not rest. It has been here longer than the oceans and the mountains and the sky, quietly producing, quietly losing a fraction of its mass to light, quietly sending its neutrinos outward at nearly the speed of light, each one a tiny, almost massless, why nearly invisible messenger passing through the whole body of the earth as though the earth were made of nothing, carrying news of a fire that never stops burning. At the edge of the solar core, where the last fusion reactions flicker outward into slightly cooler, slightly less dense plasma, a photon enters a different world. It does not travel far, not at first, not for a very long time. The plasma surrounding the core is so thick with charged particles, so dense with electrons and ions pressed against one another, that a photon, moving always at the speed of light, crosses barely a centimeter before something absorbs it. The particle that swallows it grows briefly hotter, briefly more agitated, and then releases a new photon, not in the same direction, in any direction at all. The new photon travels another centimeter, perhaps a little less, and is swallowed again. Another is born. It goes sideways, or back toward the core, or at some angle no compass would name. This is not a journey with a direction. It is a drift, vast and patient, through a medium so opaque that light itself moves through it the way a sound moves through deep water, slowly, changed at every step, arriving at last somewhere it could not have predicted from the beginning. The region the photon has entered stretches outward for more than 400,000 kilometers. It is called the radiative zone because the dominant way energy moves through it is as radiation, as light, as photons, rather than as the physical movement of material. And yet, because every photon is absorbed and re-emitted within a centimeter or so, the outward progress of any unit of energy is not the straight line rush of free light across open space. It is a random walk. 3 steps forward, 1 step back, 2 steps sideways, 1 step down, then sideways again, then up, toward the surface but only slightly, and then back. 1 centimeter, re-emitted, 1 centimeter, re-emitted. The numbers, when they are added up, become almost without meaning, but the meaning is there, under them, quiet and immense. The time it takes for energy to cross the radiative zone, to drift from the core boundary out to where the zone ends, is somewhere between 100,000 and 1,000,000 years. The spread in that estimate comes from how difficult it is to calculate exactly how opaque the plasma is to radiation at every depth, a quantity called opacity, and those calculations depend on knowing precisely what the plasma is made of. Small changes to the measured abundances of heavier elements in the sun shift the opacity estimates, and move the crossing time. The physics of that calculation is still being refined. But even the lower bound, 100,000 years, is long enough to suspend any ordinary sense of time. The light warming a face on an afternoon in summer began its crossing of this zone when the Earth was young, in human terms, during the time of the earliest stone tools, or perhaps earlier still. It has been traveling outward, centimeter by centimeter, ever since, and only now, after all of that, does it reach the surface and break free. Deep inside the radiative zone, where it meets the core, the temperature is still close to 7 million Kelvin. That is hot beyond anything experienced at any surface in the solar system, hot enough to strip electrons from any atom, hot enough that matter exists only as plasma, as a roiling gas of bare nuclei and free electrons, charged and quick and pressed against one another. And yet, despite that heat, despite that violence at the level of individual particles, the zone as a whole is still not still in the way a cold room is still, but still in a different sense, stable, unmoving, at large scales, not turning over, not churning. The temperature falls as one moves outward, but it falls gently, steadily, without the sharp drop that would set the plasma into overturning motion. The gradient is shallow enough that the dense hot plasma below has no reason to rise violently through the plasma above it. The zone is in a kind of deep thermal equilibrium, layered and undisturbed, the way a very deep ocean is layered and undisturbed, far below the surface currents. This is the condition that allows the radiative zone to exist as a distinct region. In the layer above it, which begins higher up where the temperature gradient grows steeper, the plasma will begin to overturn, hot columns rising, cooler columns sinking, the whole zone churning with slow convective motion. But here, across this great thickness of plasma, none of that happens. The material sits in its layers and lets the light pass through it in that patient, indirect way, centimeter by centimeter, year by year, century by century, millennium by millennium. A photon emitted in the core and immediately swallowed in the radiative zone is not the same photon that eventually reaches the outer edge. The original is gone. What carries the energy outward is a chain of events: absorption, re-emission, absorption, re-emission, so long and so tangled that the identity of any individual photon is meaningless. What matters is that the energy moves, slowly, erratically, but persistently outward, carried by a sequence of births and destructions that never stops. The dominant ways the plasma absorbs radiation in this zone are three. In the first, a photon is absorbed by a bound electron in an atom, an electron still attached to a nucleus, even in this hot plasma, in the cooler outer portions of the zone, and the electron is ejected, freed entirely. The atom loses an electron. A moment later, a new photon is emitted. This process is called photoionization, and it is one of the most efficient ways dense plasma holds on to the energy trying to pass through it. The second process involves a free electron, one already stripped from its nucleus, which absorbs a photon while passing near a positive ion, gaining energy, and later emits a photon as it decelerates. This is called free absorption, and it gives this kind of radiation its other name, Bremsstrahlung, from the German for breaking radiation, because it is the radiation produced by a charged particle slowing down. The third process is simpler. A photon collides with a free electron and scatters, changes direction without being fully absorbed. The energy is deflected rather than swallowed, but the effect is the same. The photon's outward progress is broken. All three of these processes work together to make the radiative zone nearly opaque to the radiation trying to cross it. The plasma is not a window, it is more like an enormous, softly glowing fog, one in which the light is always present, always moving, but never going anywhere fast. The sun's total energy output is constant as it crosses this zone. Nothing is lost. The photons are absorbed and re-emitted, but the energy they carry is conserved, passed from one interaction to the next. What changes is direction and time. The energy that left the core as gamma rays, as the highest energy photons produced by nuclear fusion, has, by the time it drifts through much of this zone, been scattered and re-emitted so many times that the average photon energy has fallen considerably. The radiation field has spread and softened. The individual photons are lower in energy, more numerous, and they fill the plasma with a glow that is not the hard, penetrating light of the core, but something more diffuse, more evenly distributed, a deep internal luminescence that the surrounding zone holds the way. Thick cloud holds sunlight, not transmitting it so much as being saturated with it. There is something in the quality of the radiative zone that resists quick description. It is not empty. It is not still in any simple way. At the scale of individual particles, it is extraordinarily busy, every electron colliding with others, every nucleus surrounded by a swarm of bound and free charges, every photon being swallowed and recreated within the span of a centimeter. The temperature, even at the outer edge, is still close to 2 million Kelvin, and yet across the whole vast thickness of it, across 400,000 kilometers of plasma, across timescales measured in hundreds of thousands of years, the thing it most resembles is patience. An enormous patience built into the structure of the material itself that slows every unit of energy and holds it close and passes it outward only in the smallest, most reluctant increments. A way to hold the scale of this is to think about what 100,000 years looks like in human terms. Every great civilization that has ever risen and fallen would fit inside 100,000 years with room left over. Every language ever spoken, every city ever built, every war and harvest and migration and forgotten song, all of it compressed into a period shorter than the time it takes for sunlight, born in the core, to drift outward through this single zone of the sun's interior. The core was making energy 100,000 years ago that has not reached the surface yet. It is on its way. It is out here, somewhere in this zone, making its random, unhurried progress through the plasma 1 centimeter at a time. The outer portion of the radiative zone grows cooler, 2 million Kelvin near the top, compared to 7 million at the base. That is still incomprehensibly hot by any earthly measure, but the gradient between those two values is the gradient that keeps the zone stable, the gentle slope that prevents the plasma from convecting, from turning over, from becoming something other than what it is. Were the slope steeper, the lower plasma would be too buoyant relative to the material above it, and it would rise. It would displace cooler plasma downward. The zone would begin to churn. But the slope is gentle, and so the zone remains layered and undisturbed across its full 400,000 kilometers. It is worth pausing at the picture of this because it is a strange and beautiful one. A sphere of plasma 500,000 kilometers in diameter, roughly 500,000 kilometers of material, rotating slowly, nearly as a single body. Not each layer at its own speed, not the equator spinning faster than the poles, but the whole mass of the radiative zone turning together with something close to the solidity of a steel flywheel, though made of plasma at millions of degrees. Helioseismology, the technique of reading the sun's interior, by the way, sound waves reverberate through it. the same way a seismograph reads the Earth's interior by the way earthquakes travel through rock, has measured this rotation and confirmed it. The radiative zone rotates with a stateliness that the layer above it will completely abandon. Below, the core generates energy and spins in the heat of its own reactions. Above, the layer waiting to receive the radiative zone's energy churns in turbulent latitude-dependent flows. But here, in the middle, the largest single region of the sun's interior holds its shape, holds its rotation, holds its layers, and passes energy outward with a patience that has no analogy anywhere in ordinary life. The atoms that make up most of the radiative zone are not, for the most part, atoms in the familiar sense. In the deepest and hottest parts, nearly everything is fully ionized, stripped bare of every electron, nuclei swimming freely in a sea of charges. As the zone grows cooler toward its outer edge, some of the heavier elements can hold on to a few electrons, the innermost ones, bound most tightly, surviving even at 2 million Kelvin. These partially ionized heavier atoms are particularly effective at absorbing radiation because they present more electron configurations that a photon can interact with. Their presence increases the opacity of the plasma, which slows the outward passage of energy further. In the 2000s, new measurements of the sun's surface spectral composition, the fingerprints left in sunlight by the elements present, revised the estimated abundances of heavier elements like carbon, nitrogen, and oxygen downward from earlier values. These revised abundances, when fed into solar models, predicted a slightly different opacity structure for the radiative zone. That different opacity structure made the models disagree with helioseismological observations, with the measured reverberations of sound waves through the sun's interior. The two pictures did not fit together cleanly. The spectroscopic models said the interior should look one way. The acoustic measurements said it looked another. That tension has not been fully resolved. Both lines of evidence are real. The data simply do not quite agree, and the reconciliation, when it comes, will refine the understanding of what the radiative zone is made of, how opaque it is, and exactly how long it takes energy to cross it. That kind of uncertainty is not a flaw. It is a sign that the science is in contact with something real, something complicated enough to resist simple description, something that pushes back when pressed. The radiative zone is not perfectly uniform in its opacity across its full depth. Near the base, the plasma is so hot and so dense that opacity is actually somewhat lower than it will be higher up. The most extreme conditions allow photons to travel slightly farther before being reabsorbed, because at the highest temperatures, the plasma becomes more transparent in certain respects. Moving outward, toward the cooler parts of the zone, the opacity rises, the mean free path shortens, and the energy diffuses more slowly. Then, near the outer edge, where heavier elements hold on to their innermost electrons, there is a particularly opaque region that acts as a bottleneck, trapping energy slightly longer before releasing it upward. None of this changes the fundamental character of the zone. It remains throughout its depth a place where energy moves not by the bulk movement of material, but by the relay of radiation through plasma, absorbed, re-emitted, redirected, passed along, one small step at a time. The photons in the radiative zone carry no memory of the core that made them. Each one is new, born from the re-emission of a particle that absorbed the photon before it, which was born from the one before that, in a chain stretching back to the fusion reactions at the sun's center. But none of that history is encoded in any individual photon. Each one is simply a packet of electromagnetic energy oscillating at a particular frequency traveling in a particular direction until something absorbs it. The chain of causation runs back through every intermediate photon to the original fusion event. But the connection is statistical, not physical. The energy is the same energy. The photon is always new. Somewhere in the middle of the radiative zone, at a depth that no probe has visited and no instrument has directly measured, the energy released in a fusion reaction that happened before recorded human history is still making its way outward. It has been absorbed and re-emitted more times than there are grains of sand on every beach on Earth. It has in some sense forgotten the shape it started with, the hard gamma ray born in a proton collision, reshaped and softened over hundreds of thousands of re-emissions into something longer, gentler, more spread out. It moves outward, centimeter by centimeter, through the patient dark of the plasma, in no hurry because hurry has no meaning here, at a pace set not by desire or direction, but by the physics of how light and matter interact in a medium this dense and this hot. That is a strange thing to sit with. Not the numbers, which resist feeling, but the image. Energy older than every human civilization still in transit, still moving, still not yet free, held inside the sun, the way heat is held inside a stone that has been warmed all day in the sun and will not cool until long after the sun has gone down. The outer wall of the radiative zone is not a physical boundary in the way a surface is. There is no membrane, no visible edge, no color change. The plasma continues from one region to the next without interruption. What changes is a single quantity, the temperature gradient, compared to the threshold at which that gradient becomes too steep for the plasma to remain in stable layers. That threshold has a name. It is called the Schwarzschild criterion, after the German physicist who defined it, and it describes the condition under which a small parcel of plasma that is displaced slightly upward will find itself lighter than its surroundings and continue to rise, rather than sinking back to its original depth. Below the threshold, the plasma sinks back. The zone is stable. Above the threshold, the plasma rises and convection begins. Throughout the radiative zone, the temperature gradient stays below that threshold. The plasma is stable. The layers hold. The energy moves through radiation alone, but as the zone approaches its outer edge, at roughly 70% of the way from the sun's center to its surface, the gradient steepens. The opacity of the plasma increases. The energy cannot diffuse outward fast enough through radiation alone, and the plasma, pressed by the energy building up beneath it and the cooling above, begins to reach the edge of instability. The boundary between the radiative zone and the layer above it is not perfectly sharp. The transition takes place across a region a few thousand kilometers thick, which is narrow relative to the 400,000 kilometers of zone below it, but still far too thick to call a line. Within that transition, the character of the sun's interior changes in more than one way simultaneously. The rotation changes. Below, across the full depth of the radiative zone, the plasma has been turning nearly as one body, equator, poles, and everything between, spinning together at essentially the same rate. Above, the plasma will spin at different speeds, depending on latitude, faster at the equator, slower at the poles, the whole layer shearing against itself in a pattern of differential rotation that is one of the most distinctive features of the sun's outer convective layer. The narrow region where these two regimes meet, where the uniform rotation of below shears against the latitude-dependent rotation of above, is called the tachocline. Thin as it is, probably less than 5% of the solar radius, thinner than the vertical distance a commercial aircraft travels while climbing to cruising altitude, Measured against the full diameter of the sun, the Tacocline is not a quiet place. The shear across it stretches and twists the magnetic field lines threading through the plasma. A field line that runs in a particular direction is grabbed by the differential rotation above and pulled laterally, stretched into a different orientation. Over time, the regular north-south pattern of the sun's large-scale magnetic field, the component called poloidal, running from pole to pole, is drawn out into rings that wrap around the sun in the east-west direction, winding tighter with each rotation. This process, by which rotation converts one kind of magnetic field into another, is one of the key steps in the generation of the sun's magnetic activity, the cycle of sunspots, eruptions, and shifts in the large-scale field that repeats on roughly an 11-year rhythm. The Tacocline is where the deep interior communicates with the outer regions by way of magnetic force. Below it, the stable, orderly radiative zone turns in uniform, quiet rotation, holding its layers, passing its energy outward in that patient, photon by photon way. Above it, the sun becomes something different, dynamic, turbulent, magnetically complicated, alive with the churning of convective cells. The Tacocline holds the seam between those two worlds. It is a seam measured in kilometers, against a sun measured in hundreds of thousands, a boundary thinner, relative to the scale of what it separates, than the membrane of a soap bubble relative to the bubble it contains. And yet across that membrane, the nature of everything changes. Rotation changes, energy transport changes, the magnetic field changes, the whole character of the plasma, from the orderly, stratified patience of the radiative zone to the overturning dynamism of what lies above, shifts within a thickness that in solar terms is barely there at all. From the other side of the tachocline, the radiative zone recedes into the interior, vast, dark, in the sense that no light escapes directly from it, filled with the slow internal luminescence of absorbed and re-emitted radiation, its layers holding steady at temperatures that drop from 7 million Kelvin at the base to 2 million at the top, its photons drifting outward in that long, directionless walk that takes 100,000 years or more to complete. The zone does not know it is a zone. The plasma does not organize itself into a named region. It simply behaves as plasma at those temperatures and densities must behave. Stable, stratified, opaque, and the behavior that results from those conditions is what physics calls the radiative zone. The energy crossing it now was made in the core while our species was still new. It has been inside the sun for all of recorded history, and longer. It will reach the surface, it will cross the outer layers and break free as light. But not yet. Out here at the tachocline, it passes through the last boundary of the deep interior and enters the churning layer above, leaving behind a world of almost unimaginable patience, a world that has been doing the same thing in the same way for billions of years and will go on doing it for billions more. The tachocline sits at its depth, invisible, without a surface to touch or a temperature to feel directly, with nothing to mark it in space except the change it contains, the rotation above turning differently from the rotation below, the magnetic shear threading through it, the boundary between two regimes of motion that are both part of the same enormous, steady, ancient star. It does not announce itself, it simply is, a seam in the deep plasma, narrow and profound, where one kind of silence gives way to another. At a depth of roughly 200,000 kilometers below the visible face of the sun, two different kinds of motion meet. One is orderly, composed, a rotation so uniform that the entire zone below turns nearly as one piece, like a great slow wheel with no preferred latitude, no faster equator, no lagging pole. The other is something else entirely. Above this boundary, the rotation begins to pull apart, the equatorial regions spinning faster than the poles, each latitude finding its own pace, the whole surface unwinding into a differential flow that no single rigid body could sustain. The place where these two regimes press against each other is thinner, relative to the sun's full diameter, than a sheet of paper pressed against the side of a basketball. It has no color, it has no edge a traveler could see, but across that invisible seam, the sun's magnetic life begins. This boundary layer carries a name borrowed from the science of ocean currents and rotating fluids. It is called the tachocline, and its thinness is part of what makes it powerful. Because the zone below rotates as one body, while the zone above rotates differentially, the material at the tachocline is perpetually sheared, the faster spinning plasma above sliding relative to the slower or differently paced plasma beside it, the way two rivers flowing at different speeds will stretch and tangle anything caught between them. Magnetic field lines that thread through this region are caught in that shear. They are stretched, they are wound. A field that once arched from one pole to the other, a simple open loop, is drawn into coils by the differential rotation above it, wrapped tighter with every solar rotation, amplified by a process that does not require any additional energy source beyond the spin itself. The stretching of a magnetic field line stores energy. It is a slow kind of tension, nothing dramatic, nothing that announces itself. The field simply grows denser, more tightly wound, holding more of itself per unit of space. And in this winding, in this quiet accumulation of magnetic pressure, the sun's most visible behavior on century-long timescales begins to take shape. The roughly 11-year cycle of solar activity, the ebb and flow of sunspots, of eruptions, of the sun's changing face, traces back here to this layer no spacecraft has ever visited and no instrument has ever touched directly. The cycle is the winding and unwinding of these fields, the amplification and eventual release of what the tachocline stores. The mechanism has a name too, and it belongs to a longer story. When a rotating body of conducting fluid stretches magnetic field lines through differential rotation, it converts a field that runs along the sun's rotational axis into one that wraps around it, a poloidal geometry becoming toroidal, the loop becoming a coil. This is the omega effect, named for the symbol used to represent angular velocity in the equations that describe it. And the omega effect is only one piece of what theorists call the solar dynamo, the full cycle by which the sun continuously regenerates its magnetic field against the tendency of that field to diffuse and weaken. The dynamo's details are still being worked out. Helioseismology, the science of tracing the sun's interior by reading the way sound waves reverberate through it, has confirmed the tachocline's existence and measured its depth, but the precise interplay of flows and fields within it remains an area of active study. What is not in doubt is that the tachocline is where the cycle originates. Everything the sun does visibly, every dark spot, every eruption, every swelling of activity and quiet retreat, begins in the shear of this hidden seam. The full activity cycle takes roughly 22 years to complete, not 11. This is because the sun's magnetic polarity reverses at each 11-year activity maximum. The north becomes south, the south becomes north, and a full return to the original configuration requires two such reversals, two such peaks and valleys, before the cycle truly repeats. The 11-year period is the half-cycle most visible in sunspot counts. The 22-year period, the Hale cycle, named for the astronomer who first recognized the polarity reversals in the early 20th century, is the full magnetic breath. Both begin in the Tococline, where the fields are born. Above the Tococline, the character of the sun changes completely. The orderly quiet of the zone below, where energy moved by radiation alone, photon after scattered photon, no bulk motion, no rising plume, gives way to something alive with movement. The plasma here does not carry energy by light, it carries it by moving. Hot material rises, cooler material sinks. The motion is driven by buoyancy, the same principle that lifts warm air above cold in an atmosphere, that drives the slow overturn of water in a pot placed on heat. But here the scale is different in every direction. The depths involved run to hundreds of thousands of kilometers. The temperatures span millions of degrees from base to top. The material is plasma, not a gas in any ordinary sense, not a liquid, but a state in which electrons and nuclei move independently, in which magnetic fields are woven through every cubic centimeter, in which the behavior of the fluid and the behavior of the field are inseparable from each other. The formal condition for this kind of convective overturn is met when the temperature falls, with height more steeply than a particular threshold. The Schwarzschild criterion, named for the physicist who worked out the mathematics of stellar stability in the early 20th century. Below that threshold, a parcel of rising gas that expands and cools will always be cooler than its surroundings and will fall back. The zone remains stable. Radiation carries all the energy. But when the opacity of the material becomes high enough that radiation alone cannot carry the energy flux demanded by the luminosity, the temperature gradient steepens until it crosses that threshold, and then the material cannot help but overturn. The plasma rises and falls not because something is pulling it, not because it has anywhere it intends to go, but because the physics of buoyancy in a temperature gradient leaves it no other option. The convective zone begins at roughly 70% of the sun's radius from the center and extends all the way to the visible surface. In absolute terms, that is a depth of approximately 200,000 kilometers, a distance that would span more than 15 Earths stacked edge to edge. And across that depth, the temperature falls from close to 2 million Kelvin at the base to roughly 5,778 Kelvin at the top. The drop is enormous. But it happens gradually, over a column so deep that the gradient at any given level is still shallow enough to seem gentle. What drives convection is not the total temperature difference, but the local rate of change. And that local rate, sustained across 200,000 kilometers, is enough to keep the entire zone churning. Within this churning, structure emerges, not chaos, but a layered organization of motion at multiple scales, nested within each other, the way cells are nested within organs, the way ripples are nested within waves. The smallest and most visible of these scales produce what are called solar granules, convective cells that tile the entire surface of the sun at any given moment, each one a few hundred to 1,000 kilometers across, each one a brief upwelling of hotter plasma that rises to the surface, spreads outward, cools and dims, and then sinks back down along its edges. The center of a granule is brighter, hotter, more elevated. The edges are darker, cooler, slightly lower, lanes of descending material that form a network of boundaries between the bright cells. From any sufficient distance, the solar surface covered in granules looks like the skin of something alive and breathing, a continuous slow texture of brightness and shadow at a scale too fine to resolve with the unaided eye, but vividly present to any instrument designed to see it. Each granule lives for roughly 8 to 20 minutes, not hours, not days, minutes, in the time it takes to watch the sun move the width of two of its own diameters across the sky, a given granule has been born, expanded, dimmed, and dissolved back into the plasma below. Another has already formed in its place, and another after that. The turnover is constant, gentle, and total, the whole surface renewing itself on a time scale no longer than a quiet morning. There are, at any moment, on the order of 4 million of these cells covering the solar surface, each one an overturn of plasma, each one a small piece of the engine that carries the sun's heat towards space. Individually, they are brief. Together, they are the face of something that has been running without pause for 4.5 billion years. Above the granulation scale, a larger pattern of horizontal flow organizes the surface. These larger cells, called supergranules, span roughly 30,000 kilometers from one side to another, roughly 2.5 times the diameter of the Earth. They are not visible in brightness, the way granules are. The temperature difference between the center and the edge of a supergranule is too small to detect with ordinary light. What reveals them is the motion of plasma across the solar surface, a slow horizontal drift of material from the center of each cell toward its edges, detectable through the Doppler shift of spectral lines in the light the surface emits. Where that light is shifted toward shorter wavelengths, the plasma moves toward the observer. Where it shifts toward longer wavelengths, the plasma moves away. The pattern of these shifts mapped across the solar disk traces the outlines of supergranular cells as clearly as a topographic map traces valleys. Supergranules persist for 1 to 2 days before they too dissolve and reform. Their edges, the downflow lanes where the horizontal motion converges and sinks, are where the sun's small-scale magnetic field concentrates, swept there by the surface flows, the way flotsam is swept toward the edges of slow eddies. The network of these edges forms a mesh of magnetic enhancement that covers the whole surface, slightly brighter in certain ultraviolet wavelengths, faintly visible to instruments sensitive enough to detect it. The supergranular network is not where the sun's large-scale active region fields live. Those are deeper, more concentrated, rooted in the tachocline. But the network is where the quiet background field of the solar surface organizes itself, and it shapes the chromosphere above in ways that become visible at certain wavelengths of light. Deeper in the convective zone, beyond the reach of any direct Doppler measurement, theory predicts still larger convective structures, flows on scales of hundreds of thousands of kilometers, slow overturning circulations that would take weeks or months to complete a single cycle. These have been called giant cells. If they exist in the form theory suggests, their influence on the solar dynamo could be significant, deep flows carrying magnetic flux from one latitude to another, redistributing the products of the tachocline's field amplification across the solar interior. But the observational evidence for giant cells is ambiguous. Helioseismological surveys designed to detect them have returned results far weaker than models predicted, hints, not confirmations. The solar interior at this depth moves in ways that leave a surprisingly faint imprint at the surface, and the large-scale flow structure of the deep convective zone remains one of the genuinely open questions in solar physics. The best current picture suggests that the deep convection is real, but organized differently from what early theory expected. The details are still being worked out. There is also a flow that operates at the global scale, not a convective cell, but a slow meridional circulation that carries surface plasma from the equator toward the poles, where it sinks, moves through the interior, and returns toward the equator along the base of the convective zone. This circulation is gentle, averaging a few meters per second at the surface, fast enough to complete a full circuit in something between a decade and 2 decades, depending on latitude and depth. It is one of the ingredients in the solar dynamo, carrying the remnants of magnetic active regions from mid-latitudes toward the poles, contributing to the reversal of the polar fields that marks each activity maximum. The meridional flow is measured at the surface through Doppler techniques, but its behavior at depth, where it turns and returns, is harder to determine. Different methods of helioseismological inference have returned somewhat different answers, and reconciling them is ongoing work. It matters because the speed and depth of this return flow affects how quickly the dynamo cycle runs, and therefore the length of the activity cycle. The interplay of all these flows, the differential rotation inherited from the tachocline, the convective overturn at multiple spatial scales, the meridional circulation at global scales, produces a convective zone that is neither the simple boiling pot picture nor the fully worked out system that theorists once hoped. It is a place of real complexity, partially observed, partially modeled, with several first-order questions still open. This is not a failure of science. It is an accurate account of how interior fluid dynamics in a star resists easy characterization. The Sun is the only star close enough to study in this detail, and even at this detail, the interior keeps significant portions of its behavior to itself. What the convective zone does deliver, unambiguously, is the Sun's luminosity to the surface. All of the energy that began as the mass equivalent of 4 hydrogen nuclei in the core that wandered the radiative zone for longer than human civilization has existed, arrives at the base of the convective zone and is carried the rest of the way by the bulk motion of plasma. Radiation is no longer the dominant mechanism. The material itself moves, and it carries the heat. Convective velocities near the surface can reach 1 kilometer or 2 per second, fast by the standards of a body moving through dense plasma, though slow compared to many other solar processes. At the base of the convective zone, where the material is denser and more viscous in the relevant sense, the convective velocities are smaller, but the energy flux they carry is the same. The area is larger at the base than at the surface, and the depth compensates for the slower motion. The magnetic field throughout the convective zone is not passive. The motion of electrically conducting plasma through a magnetic field generates currents. Those currents create new magnetic fields. The fields resist or redirect the plasma motions, and those redirected motions generate still more field. The feedback between fluid and field is continuous and nonlinear. The same general class of behavior that produces complexity and sensitivity to initial conditions in other coupled systems, but here operating in 3 dimensions through a sphere 200,000 kilometers deep, driven by the steady engine of convection below and shaped by the tachocline's amplified fields at the base. The result is a magnetic field on the solar surface that is deeply structured, not a uniform dipole, but a patchwork of concentrated and diffuse regions, of strong localized fields and quiet background network fields, constantly shifting and evolving on timescales from minutes to years. In regions where the magnetic field beneath the surface is strong enough, it changes the local behavior of convection in the zone above. Strong field resists convective motion across field lines. Where the field is concentrated into a flux tube, a rope of aligned magnetic field threading vertically through the convective zone, the plasma inside the tube is partially isolated from the convective overturn outside it. The tube carries a different temperature profile. It can be darker or brighter than its surroundings, depending on the geometry and the depth. When such a tube rises to the surface and emerges into the photosphere, it appears as a region of suppressed convection and reduced brightness, a sunspot visible to even ancient observers as a dark mark on the solar face. But the emergence itself begins here, in the convective zone, where the flux tube has been rising buoyantly through the plasma for days or weeks before it reaches the surface. The photosphere is where the emergence becomes visible. The convective zone is where the tube has been traveling. Alongside the small-scale turbulent convection and the large-scale meridional flow, the convective zone sustains the propagation of sound waves and surface gravity waves that propagate through the solar interior and ring the sun like a great slow bell. These are the waves that helioseismology uses to probe the interior, waves generated by the buffeting of convection propagating through the sun on paths that depend on the sound speed at each depth and refracting upward as the sound speed decreases near the surface. Where they strike the surface, they create the 5-minute oscillation, a gentle rising and falling of the photosphere at periods near 300 seconds, measurable as Doppler shifts far smaller than a meter per second. The pattern of these oscillations, decomposed into millions of individual modes of vibration, encodes information about the temperature, density, and rotation of the interior at every depth. It is the primary tool by which the Takalk was localized, by which the base of the convective zone was placed, by which the internal rotation was mapped. Without helioseismology, the structure described here would be entirely theoretical. With it, the theory is tested, confirmed in its broad strokes, and challenged in its finer details. The convective zone is also where the sun's acoustic power is generated, where the turbulent convection stirs the plasma strongly enough to send pressure waves propagating in every direction. Most of these waves reflect at the surface and spend their energy in the interior. Some carry energy upward into the chromosphere and corona above, where they may contribute, through mechanisms still under study, to the heating that makes the sun's outer atmosphere so much hotter than its surface. The connection between what happens in the convective zone and what happens in the atmosphere above is not a simple handoff. It is a deeply coupled system with flows and fields and waves crossing the photospheric boundary in both directions, the convective zone and the atmosphere above influencing each other continuously. The temperature at the top of the convective zone, the photospheric temperature, roughly 5,778 Kelvin, is both an end and a beginning. It is where the convective overturn gives way to the thin layer of the photosphere, where the plasma becomes transparent enough to let photons escape, where the long interior journey of energy ends and the 8-minute journey to Earth begins. But it is also where a new set of processes begins, processes that operate in the atmosphere above the surface, in the chromosphere and the corona, in the streaming solar wind. The convective zone does not merely deliver energy to the surface, it delivers fields, it delivers flows. It delivers the organized, tangled, continuously regenerated magnetic structure that shapes everything the sun does above its photosphere. The outer atmosphere of the sun is, in a real sense, the continuing expression of what the convective zone has made. Standing at the very top of the convective zone, at the threshold where the rising plasma of the last convective cells gives way to the photosphere, there is a quality of arrival that the physics itself seems to mark. The density has fallen by many orders of magnitude from the base. The temperature has dropped from near 2 million Kelvin to near 6,000. The dominant energy transport mechanism has shifted from the bulk motion of plasma back toward radiation as the opacity of the material finally falls low enough for photons to travel meaningful distances without being absorbed and scattered. The granules visible at the photospheric surface are the tops of the convective cells, the upwelling parts of the last overturns before the material cools and becomes transparent. They are the convective zone's final gesture, its last visible expression before the light it has carried for so long passes through into open space. The churning that fills the 200,000 kilometers below does not stop abruptly. It slows, it thins, it becomes the granulation pattern at the surface, then gives way to the quiet shimmer of the photosphere, then to the still stranger temperature structure of the chromosphere above. But the energy that was moving through that churning column, the energy that drove every overturning roll, every rising hot plume, every sinking cool lane, that energy is now light, crossing the last few hundred kilometers of the sun's surface, about to be free. From the tight quarters of the core, through the long stillness of the radiative zone, through the deep churning column of the convective zone, the sun has carried this energy upward for an almost incalculable time, and at the very top of the convective zone, the last rising cells deliver it gently to the surface, and the surface lets it go. The sun at this boundary is neither the dense opaque interior nor the tenuous outer atmosphere. It is the seam between those two worlds, as thin relative to the full solar radius as a coat of paint on a globe, and across that seam the character of the sun transforms completely. Below, motion, pressure, opacity, the slow conveyor of matter carrying heat. Above, light flowing outward at last without obstruction into the space between the sun and everything it illuminates. The convective zone ends here quietly, without drama, the way a river ends at the sea, the motion continuing, the form dissolving, the energy that was always moving, now simply moving in a different way. The photosphere begins not with a boundary drawn in space, but with a texture, 4 million granules pressing against one another across the entire face of the sun, each one roughly as wide as a small country, each one burning and dissolving, and being replaced within the span of a quarter of an hour. From far enough away, the solar disk appears to have a clean, sharp edge, a circle precise as a coin. Closer, that edge dissolves into a shell of luminous gas no thicker, relative to the sun's full width, than the skin stretched over a piece of fruit. The sun has a radius of nearly 700,000 kilometers. In the photosphere, the layer from which all its visible light finally escapes, reaches barely 500 kilometers from top to bottom. In that thin band, something that has been trapped and redirected for an immense span of time at last finds open space. The surface does not hold still. Every granule is a convective cell, hot plasma rising through the center, spreading outward, cooling at the edges, then sinking back below along darker lanes that divide one cell from the next. Seen in the right kind of light, the photosphere looks like a vast and slowly seething mosaic, always moving, always renewing, always the same in its broad character, and never the same in its specific arrangement. Each bright center is hotter than the darker border surrounding it, and that temperature difference, a few hundred Kelvin across a distance of 1,000 kilometers, is enough to make the contrast visible from 150 million kilometers away. The dark lanes are not cold, they are simply less hot. Against the full brightness of the rising plasma, even a small dimming registers as shadow. The rising center of a granule reaches temperatures close to 6,000 Kelvin. The sinking edges fall to something nearer 5,500 Kelvin. In the context of the deep interior, where temperatures climb into the millions, this is an almost imperceptible difference. But the photosphere is the sun's outermost working layer, the place where density has dropped low enough that photons can finally decouple from the plasma and travel freely, and at these scales, even small temperature differences carry enormous consequences for the light being produced. Every square meter of the photospheric surface pours energy outward at a rate that no object humans have built can approach. And yet the sun achieves this not through any single extraordinary event, but through the quiet accumulation of millions of individual convective cells, each contributing its modest brightness to a surface that together blazes with the combined output of 4 million separate slow boilings. Each granule lasts between 8 and 20 minutes. Then the hot material has spread, cooled, and sunk, and the whole cell collapses. Where it was, another rises. The photosphere has looked very nearly the same for billions of years, not because nothing changes, but because the rate of change is itself steady, the cells appearing and dissolving in roughly equal numbers at every moment, so that the total pattern holds even as every individual element within it is continuously replaced. It is a kind of permanence made entirely of transience. The surface endures because it never stops replacing itself, granule by granule, minute by minute, across an area of more than 6 trillion square kilometers. The photosphere's average temperature, taken across its full breadth and integrated into the light it produces, works out to 5,778 Kelvin. That number comes from a simple physical relationship, the same relationship that governs the glow of every hot object applied to the sun's total light output and its measured size. It places the photosphere in a regime where most of its energy is radiated as visible light, with the peak of its emission falling at a wavelength of roughly 502 nanometers. That wavelength sits in the green portion of the visible spectrum. The sun emits more green light than any other color, by a small but real margin, when measured purely in terms of photons per unit wavelength at the peak. And yet the sun does not appear green. The spectrum of the photosphere is broad enough that it spans the full range of visible wavelengths, from deep red through to the edge of violet, and the human eye integrates that spread into something perceived as white, or in certain atmospheric conditions as a warm yellow gold. The greenness is real and measurable. It is simply invisible, buried inside the completeness of the sun's output. Below 5,778 Kelvin, the photosphere cannot sustain its optical thickness. Above it, the plasma is denser, hotter, more opaque. The photosphere is the precise region where the solar gas transitions from opaque to transparent, where a photon moving outward finally has a good chance of escaping rather than being immediately absorbed and re-emitted. Physicists define this transition point as occurring at an optical depth of 2/3. At optical depths greater than 2/3, the solar material remains effectively opaque to the photons trying to pass through it. At depths shallower than 2/3, the plasma is thin enough that light can travel freely. The photosphere sits exactly at this threshold. It is not really a surface at all, in the way that the ground is a surface or the ocean is a surface. It is the depth at which the sun becomes transparent, and everything above it is what we call the atmosphere. The density at this threshold is extraordinarily low. The photospheric plasma has a density of roughly 2/10,000ths of a kilogram per cubic meter, about 1,000 times less dense than the air at sea level on Earth. An object moving through the photosphere would feel almost nothing. The material is so thin, it barely registers as anything solid, or liquid, or even gaseous in any familiar sense. And yet this tenuous plasma remains optically thick. It absorbs and re-emits photons efficiently enough to prevent light from simply streaming through it in straight lines. And that opacity is what makes the photosphere the visible surface of the sun. The sun's face is not a place where matter ends. It is a place where matter becomes too thin to be opaque. The photosphere is also where the sun becomes measurably darker at its edges. Looking at the center of the solar disk, a line of sight passes through the photosphere and terminates in the deeper, hotter, denser layers below. The photons arriving from the center of the disk come from a relatively deep, hot region. Looking toward the edge of the disk, the limb, the geometry changes. A line of sight toward the limb passes through the photosphere at a shallower angle, spending more of its length in the upper, cooler, thinner gas before the path ends. The photons arriving from near the limb originate in higher, cooler layers. They are slightly dimmer and slightly redder. The result is a gradual shading across the disk from a brighter center to a softer, dimmer edge. This shading has a name, limb darkening, and it reveals simply by looking at the sun's face that the photosphere has a temperature structure growing cooler with height. Limb darkening is not subtle. It is visible to the naked eye when the sun is dim enough to observe directly, as it sometimes is near the horizon through thick atmosphere. The disk is not uniformly bright. The center holds more light. The edges fall away gently, giving the sun its unmistakable spherical quality in photographs taken with proper filters. That sense of a globe rather than a flat disk, of depth behind the surface rather than a coin pressed against the sky. The wavelength dependence of limb darkening, the fact that the dimming is stronger at shorter wavelengths than at longer ones, has made it one of the earliest precise tools for probing how temperature and density change with height through the photosphere. The sun offers its own profile simply through the way it shades toward its edges. Somewhere within the photosphere, embedded in its lower and middle depths, there are features that disrupt the otherwise continuous granulation in a way that has been observed for centuries. These are regions where the magnetic field, generated far below in the convective zone, rises through the solar interior in concentrated bundles and emerges at the surface. Where a strong enough field breaks through, convection is suppressed. The field lines are dense enough to resist the churning motion that drives granulation everywhere else. Without the constant delivery of hot material from below, the local temperature drops, the region cools relative to its surroundings, and far away, against the brilliant photosphere, a cooled region appears dark. These are sunspots. A sunspot's darkest central region, called the umbra, sits at a temperature of roughly 3,500 to 4,000 Kelvin. The surrounding photosphere burns at more than 5,700 Kelvin. That difference of nearly 2,000 Kelvin means that umbra radiates dramatically less energy than the surface around it, and so it registers to the eye as a dark island, sometimes nearly black against the solar disk. If an umbra could be seen in isolation, removed from the context of the photosphere surrounding it, it would glow brilliantly, as brightly as iron heated to incandescence, far surpassing any artificial light. The darkness is not absolute. It is comparative. The photosphere is so bright that anything even somewhat cooler is swallowed by the contrast. Sunspot umbrae contain magnetic fields measuring thousands of Gauss, thousands of times stronger than the average magnetic field found across the quiet photosphere. The field is strong enough not just to suppress convection locally, but to shape the plasma around the umbra into a broader textured structure. Surrounding the umbra there is a lighter ring called the penumbra, crossed by long thin filaments that run roughly radially outward from the dark center. These filaments are regions of slightly less suppressed convection, where the field is strong, but not quite strong enough to halt all upward motion. The penumbra is intermediate, cooler than the quiet photosphere, warmer than the umbra, organized into a fine structure that gives sunspots their characteristic layered appearance. The magnetic field threading through a sunspot umbra emerges nearly vertical at the center, then fans outward and becomes more inclined through the penumbra, like the bristles of a brush pressed against a table, spreading outward from the central point of contact. Below the surface, the field is concentrated into a tube, a column of magnetized plasma that threads downward through the photosphere into the convective zone beneath. Where two sunspots appear near each other, they are often connected by an arch of field lines that loop up through the photosphere and out above it, through the chromosphere and into the corona. These arching structures can span hundreds of thousands of kilometers. They are the foundation of much of the solar atmosphere's dramatic behavior. But all of that begins here, at the photosphere, where the field first breaks the surface. Sunspots do not stay fixed in place. They form over hours to days, grow, evolve, and decay over periods of weeks, and the whole population waxes and wanes over a cycle of roughly 11 years. Near the peak of the cycle, the photosphere can host dozens of individual spots at once, organized into complex groups that sometimes cover areas many times the size of Earth. Near the low point, the photosphere can go weeks with no spots at all, its face returning to uninterrupted granulation, quiet and uniform from one limb to the other. The cycle itself is tied to the deep structure of the sun's magnetic field, to the shear and amplification occurring in the layer below the convective zone, but its signature is most plainly read in the photosphere, where each emerging field bundle marks itself in shadow against the surrounding brightness. The photosphere also contains, in its layers, a wealth of fine structure, visible only with careful observation. Bright points appear between granules, particularly in regions where weak magnetic field concentrations gather into the dark intergranular lanes. These faculae, or bright points, are slightly hotter than their surroundings, and become more visible near the solar limb, where the geometry of limb darkening makes the surrounding photosphere relatively dim, and these hotter structures stand out in contrast. Near the limb, faculae can brighten the disk slightly, even as sunspot groups darken it elsewhere, and the interplay between these effects contributes to the very small variations in the sun's total light output over the activity cycle. At any given moment, the photosphere is simultaneously doing all of these things, granulating continuously, hosting sunspots in whatever configuration the current phase of the cycle has produced, threading with small-scale magnetic bright points, and dimming systematically toward its edges through the depth-dependent temperature gradient revealed by limb darkening. The surface is never fully at rest. It is never in full chaos. It holds a statistical regularity across its enormous area, a steady mean behind the constant local variation, the way a large crowd holds a constant noise level even as each individual voice within it rises and falls. The sun rotates, but because the photosphere is plasma rather than solid rock, different latitudes rotate at different speeds. The equatorial photosphere completes a full rotation in roughly 25 days. At latitudes near 60 degrees, the same rotation takes about 31 days. This differential rotation, faster at the equator, slower toward the poles, is one of the photosphere's defining characteristics, and it is the source of the steady winding and stretching of the magnetic field lines that thread through the surface. A field line that begins oriented roughly from pole to pole will, over the course of weeks, be stretched and inclined by this differential rotation until it runs more nearly east-west. This winding is part of the deep process that amplifies the field and drives the activity cycle, and the photosphere is where this winding can be directly measured by tracking the motion of sunspots across the disk. The spectrum of light produced by the photosphere contains not only the broad thermal continuum, but also thousands of narrow absorption lines, wavelengths at which specific atoms and ions in the outer photosphere and lower chromosphere have absorbed some of the light passing through. These lines are called Fraunhofer lines, after the German physicist who mapped them systematically in the early 19th century. The sodium D line, the hydrogen Balmer series, the calcium H and K lines, each one a dark gap in the spectrum corresponding to a precise transition between energy levels in a specific type of atom. Together, these lines encode the full chemical composition of the solar photosphere. From them, scientists have measured the abundance of nearly every element in the solar surface, overwhelmingly hydrogen, with helium as the second constituent, and all other elements present in small but precisely determined fractions. The light leaving the photosphere is not entirely smooth, even beyond the Fraunhofer lines. 5-minute oscillations, global resonances of the entire sun, driven by convective motions and detected as Doppler shifts in photospheric spectral lines, rise and fall across the disk in patterns that reflect the interior structure through which the waves have traveled. This is helioseismology, the practice of reading the sun's interior from the ringing of its surface, the way the internal composition of a bell can be inferred from the tone it produces. The photosphere is not only a radiating surface, it is a membrane through which the deep sun communicates its structure in vibration. Looking at the photosphere across the full width of the solar disk, in the particular wavelength of red light emitted by hydrogen atoms, called hydrogen alpha light, the surface comes alive with detail. Filaments appear, dark threads of cooler plasma suspended in the magnetic field above the photosphere. Active regions glow brighter around sunspot groups, where the field has heated the overlying gas. The granulation resolves into its full cellular texture, every cell distinct, the dark lanes between them crisp and fine. In white light, without any filtering for a particular wavelength, the disk is a single brilliant expanse, broken only by the darker islands of sunspots and the subtle gradient of limb darkening. The photosphere in hydrogen alpha is a different world, detailed and structured, and magnetically sculpted at every scale. The photosphere is also the layer from which the sun's gravitational and magnetic fields extend outward into space. The gravity that holds the solar system together originates in the mass of the sun spread through all its layers, but the photospheric surface is the outermost point at which that mass exerts its organizing influence on the plasma layers above, without itself being supported by those layers. Above the photosphere, the gas is so thin that it cannot support the kind of hydrostatic equilibrium maintained deeper in the sun. The layers above are held in place not by pressure balance alone, but by the magnetic field threading up through the photosphere. From below, the dynamic effects of wave propagation and the outward flow of energy and plasma. The photosphere is, in this sense, the final floor of the sun's main body, the last level at which ordinary thermal pressure and gravity keep each other in balance. The photosphere is also the origin of the solar irradiance that reaches Earth. The total amount of energy arriving at the top of Earth's atmosphere per unit area is called the solar constant. Though it is not quite constant, it varies by roughly 0.1% over the solar cycle, rising slightly at solar maximum due to the increased contribution of faculae and active region emission, falling slightly at solar minimum as sunspot groups diminish and facular brightness fades with them. These variations are small in absolute terms. Over the time scale of a human life, they are nearly imperceptible as changes in the sun's brightness. Over the time scale of the sun's long history, however, the photospheric output has changed substantially. The young sun was significantly less luminous than it is today. Over 4.5 billion years, The photospheric temperature and brightness have climbed as the core's helium fraction has grown, changing the pressure balance throughout the solar interior and causing the photosphere to sit at a slightly higher temperature and higher radius than it once did. Within the photosphere's 500-kilometer depth, the transition from opacity to transparency is not sharp. It happens gradually, over a range of heights, with the effective radiating layer shifting depending on the wavelength of the light being observed. At wavelengths where the photospheric plasma is more opaque, near strong absorption lines, or in the ultraviolet, the effective surface from which photons escape sits higher, in cooler gas. At wavelengths where the plasma is more transparent, in the infrared or in the wings of spectral lines, photons escape from deeper, hotter layers. This is why the center of an absorption line in the solar spectrum appears darker than the surrounding continuum. Light at that wavelength comes from higher, cooler gas, and cooler gas radiates less. The photosphere is not a single fixed surface, but a range of depths that different wavelengths sample differently, each one reading a slightly different temperature, a slightly different height, a slightly different view into the underlying structure. The low density of the photosphere, that figure of roughly 2/10,000ths of a kilogram per cubic meter, means that the mean free path of a photon at the photospheric level, though still short, is finally long enough for light to stream outward rather than taking a continuous random walk. Below the photosphere, the mean free path is measured in fractions of a centimeter. Within the photosphere, it grows. Just above the layer defined by an optical depth of 2/3, a photon can travel hundreds of kilometers before being absorbed. The step from trapped to free is gradual rather than abrupt, but it is decisive, and it is what gives the photosphere its nature as the visible face of the sun, rather than just another opaque interior shell. A volume of the photosphere no bigger than a house would weigh almost nothing. The plasma is so diffuse that it would barely register on any ordinary scale, and yet it is this thin, barely there layer of hot gas that produces essentially all of the light the sun sends into the solar system, all the light that grows Earth's plants, warms its oceans, drives its weather, and makes its days. The deeper layers generate the energy. The convective zone carries it upward, but the photosphere is where that energy is converted into light, where it breaks free of the material that produced it and becomes something that can cross 150 million kilometers in 8 minutes and arrive at a leaf or a retina or a solar panel, unchanged in its essential nature from the moment it departed. The granulation covering the photosphere is the final expression of the convective motion below. Each rising column delivers hot material to the surface, where it spreads outward and radiates freely into space for the first time. The cooling that drives the column back down is caused by this radiation, the plasma losing energy to the open sky, becoming denser, and sinking back below the surface to be reheated. The photosphere does not radiate in spite of convection. It radiates because of convection. The two are the same process viewed at two different moments, the bulk motion of plasma below and the emission of photons at the surface above. The sun's visible disk, seen from Earth, is a circle of steady light about half a degree across in the sky, smaller than the circle covered by the tip of a finger held at arm's length. Within that circle, at any moment, 4 million granules are rising and cooling and sinking. Dozens of sunspot groups may be present, or none. Faculae brighten the limb in scattered patches. 5-minute oscillations ripple across the entire disk in patterns detectable only through precise spectroscopy. The spectrum emitted by the photosphere carries thousands of absorption lines, encoding the composition of the solar gas, and embedded in those lines are Doppler shifts from the oscillations, from convective motions, from the differential rotation of the disk. The photosphere holds in its light an extraordinary record of the state of the entire sun, surface, interior, atmosphere, and magnetic field, all encoded in the wavelengths of the photons that finally broke free from the plasma and began their 8-minute crossing of the space between the sun and its nearest planet. Standing in open sunlight, the warmth on the skin arrives from photons that left the photosphere roughly 8 minutes before. They cross the full width of interplanetary space in that time, having spent something between tens of thousands and a million years, slowly working their way through the dense solar interior before reaching the photosphere and escaping. At the photosphere, everything that slow migration produced, that immense span of absorption and re-emission, that grinding upward drift through plasma so thick a photon could barely move, suddenly ends. The density drops below the threshold needed to trap light. The material opens, and a photon born from the conversion of mass to energy in the deepest part of the sun finds, for the first time, nothing in its way. The photosphere holds all of this quietly. It does not announce itself. It simply glows, a thin, luminous shell around a vastly more massive interior, producing at its threshold the light that makes everything visible in the inner solar system, and then releasing that light into a space that offers it no resistance at all. The energy travels freely from that point. The plasma it leaves behind continues to granulate, continues to host sunspots and bright points, continues to ring with oscillations from below, and to absorb spectral lines from atoms in the thin gas just above its surface. The photosphere goes on doing what it has done for nearly 5 billion years, its granules forming and dissolving in their steady rhythm, its light streaming outward in every direction, constant in its long average and always in motion in its fine detail, a surface that is never twice the same and never anything other than what it is. And then, at the very top of the photosphere, at that thin and barely perceptible altitude where the optical depth has fallen to 2/3, and the plasma has finally grown thin enough to let light pass through unchecked, a photon crosses the threshold. It has been absorbed and re-emitted an almost uncountable number of times. It has been redirected in every direction the laws of physics allow. It has carried energy, generated in the solar core, across the full interior of the sun, through the dense radiative zone, through the churning convective envelope, through the final granulating layer at the solar surface. Now, for the first time in its long and indirect existence, it travels in a straight line, outward into the dark, at the speed of light, free of the plasma that made it, free of every absorption and every redirection. The photosphere releases it without ceremony. It is one of many. The sun produces them in numbers so large the language of ordinary counting cannot hold them. But this one is free, and the space ahead of it is open, and it will not stop until something stops it. During a total solar eclipse, in the few breaths between the last sliver of photosphere vanishing and the corona flooding the sky with its pale, silent fire, a thin rose-red ring appears at the sun's edge. It lasts only a moment. It glows in a color so precise, so unmistakably warm against the blue-black of a suddenly darkened day, that observers who have waited years for this moment often forget to breathe. That color, the deep, soft red of hydrogen releasing light, rises from a layer of the sun that sits just above the visible surface, thin enough that ordinary sunlight washes it invisible, close enough to the photosphere that it has borrowed the name, the sphere of color, the chromosphere. And it is the first of three layers that stretch between the place where light escapes and the place where the sun fades, slowly into the space between the planets. The chromosphere begins where the photosphere ends, and for a few hundred kilometers, the temperature continues to fall, the way a hillside descends past the last tree line into open rock. It drops to a minimum of somewhere around 4,100 or 4,400 Kelvin, cooler than the visible surface, before something changes. Before the temperature, without any obvious source of heat below, begins to climb again. It rises through 8,000 Kelvin, through 20,000. By the time it reaches the chromosphere's outermost edge, the gas glowing there is nearly 20 times hotter than the photosphere below it. Simple thermal logic says this cannot happen. Heat flows from hot to cold. A fire does not warm the air above it to temperatures greater than the flame itself. And yet here, 2,000 kilometers above the visible sun, the plasma is hotter than the surface it floats above, and the heat keeps rising. The chromosphere's red glow comes from hydrogen. A hydrogen atom, excited by the environment around it, can absorb energy and push one of its electrons up to a higher orbit, held there briefly before the electron falls back down. When an electron falls from the third orbit to the second, the atom releases a single photon of light at precisely 656 nanometers, a deep, clean red. Multiply this event by trillions upon trillions of hydrogen atoms doing it simultaneously across a layer thousands of kilometers deep, and the result is the color that eclipse watchers wait years to see. It is not decoration. It is a record of electrons returning to rest, of atoms giving back the energy they briefly held, of a temperature gradient steep enough to keep this process running continuously at every moment across the entire face of the sun. Spicules rise through the chromosphere in their hundreds of thousands. Each one is a narrow column of plasma, roughly 500 to 1,000 kilometers wide, which is the distance from one edge of a moderate country to another, and each one erupts upward at speeds between 15 and 30 kilometers per second, reaching heights of 5,000 to 10,000 kilometers before collapsing and dissolving back into the chromospheric background. At any given moment, something near 100,000 spicules stand on the solar surface, rising and falling like slow geysers in slow time, each one lasting perhaps a few minutes before the next takes its place. From a distance, the chromosphere's surface, seen in the narrow wavelength of hydrogen alpha light, looks like a field of pale grass in a wind, the spicules bending, stretching, dissolving, and reforming in a quiet, continuous restlessness. They carry mass and energy upward from the lower atmosphere. Some of that energy finds its way into the layers above. Above the chromosphere, the temperature climbs so fast that the distance over which it does so barely registers on any scale used to describe the sun. A few hundred kilometers less than the altitude at which the satellites that carry weather images orbit the Earth, and the temperature leaps from 20,000 Kelvin to over 1 million. This is the transition region, and it is one of the steepest thermal gradients found anywhere in the observable universe. The plasma crossing it undergoes a transformation so radical that the atoms themselves change character. At 20,000 Kelvin, some atoms still hold most of their electrons. At 1 million Kelvin, carbon is missing 4 of its 6 electrons, oxygen has lost 5 of its 8, silicon is stripped of 3, and all of them emit light far beyond the violet end of the visible spectrum, deep in the ultraviolet, and beyond into the extreme ultraviolet. This light cannot reach the ground. The atmosphere absorbs it. It can only be seen from space, and the instruments that have been built to record it show a sun that looks nothing like the warm yellow disk familiar from Earth, a sun of arcs and sheets and concentrated streams, every structure in it, controlled by magnetic fields too fine to see and too strong to resist. The transition region is thin because it has to be. At the temperatures where hydrogen becomes fully ionized, the way plasma radiates heat changes abruptly, and the plasma cools faster than it can be resupplied from below. So it cools quickly, and the temperature falls, except that it does not. Something keeps feeding it. Something upstream of the corona keeps pushing energy downward through this narrow gap, maintaining the gradient, sustaining the transition, holding the million-degree plasma above and the 20,000-degree plasma below in a relationship that simple conduction would dissolve in minutes. What that something is remains the central question of solar physics. The corona begins where the transition region ends, and from there the temperature climbs further still. Across the corona's vast, diffuse extent, a region hundreds of thousands of kilometers thick, stretching far beyond the visible edge of the sun, the plasma holds steady at 1 to 3 million Kelvin in quiet regions and rises above 10 million Kelvin in the arching structures that loop over active areas. The corona is so hot that its atoms are stripped of nearly all their electrons. It is so diffuse that the total energy it contains, spread across that enormous volume, is far less than the energy in the photosphere below. But its temperature, the average speed of its individual particles, is among the highest of any large-scale structure in the solar system. For a long time, the corona's extreme heat was a mystery without even a name, because the corona itself was barely known. The pale halo visible during total solar eclipses had been observed and drawn for centuries, but its nature was uncertain. Some astronomers thought it was a feature of the Earth's atmosphere or scattered light from the moon. The corona's spectrum offered clues, but the clues were confusing. Beginning in the late 19th century, observers recording the corona's spectrum noticed an emission line in the green part of the spectrum, a bright, precise line that did not match any element known on Earth. For decades, it was attributed to a hypothetical element unique to the Sun, provisionally named coronium, the way the element helium had been identified in the solar spectrum before it was found on Earth. But coronium never materialized. No one could isolate it in a laboratory. No theoretical framework could accommodate a new element with a spectral line at that position. The answer arrived in 1941. The German-Swedish physicist Bengt Edlund, working with a body of spectroscopic data that had accumulated across decades, and drawing on calculations by the French astronomer Walter Grotrian, identified the green emission line as iron, not ordinary iron, iron that had been stripped of 13 of its 26 electrons, leaving an ion so highly charged that it emitted light at a wavelength utterly unlike neutral ions. To strip 13 electrons from an iron atom requires temperatures not of thousands of Kelvin, but of millions. The corona's mysterious green line was not the signature of an unknown element. It was the signature of an ordinary one, pushed by heat into a state no terrestrial laboratory had yet reached. In that identification, the temperature of the sun's outer atmosphere became undeniable, and the question of where that heat comes from became urgent. The corona's heat is still not fully explained. Two ideas carry the most weight, and both may be partly right. The first centers on Alphen waves, a kind of oscillation that travels along magnetic field lines, the way a ripple travels along a plucked string. Convection below the photosphere is turbulent, and that turbulence constantly tugs and shakes the magnetic fields that thread up through the solar surface. Those disturbances propagate outward along field lines as waves, and if the waves dissipate their energy in the corona, if they transfer their motion into heat, they could, in principle, Maintain the corona's temperature. The second idea belongs to Eugene Parker, who in 1988 proposed that the corona is heated not by large continuous waves, but by countless tiny events of magnetic reconnection, where magnetic field lines of opposing orientation come close enough together, they can break and reconnect in a new configuration, releasing a burst of energy. Each individual event is too small to observe directly. Parker called them nanoflares. If they occur frequently enough, across enough of the corona simultaneously, their combined output might sustain the heat that Edlund's identification had made necessary. Both hypotheses are being tested by spacecraft that have gone closer to the Sun than anything before them. One of them left Earth in 2018, designed to approach within a few million kilometers of the solar surface, well inside the corona itself, to measure the magnetic field, the particle velocities, the wave structures, and the fine-scale magnetic dynamics directly. Another, launched in 2020, carries instruments that can observe the solar wind and the corona from a position that moves closer to the Sun than any previous imaging mission. The data they return is still being processed, still being interpreted. The answer, when it arrives, will be a quiet thing, a pattern in numbers, a confirmation that one model fits and another needs revision, but it will resolve a question that sat unanswered for 80 years. In the meantime, the corona continues. It glows in extreme ultraviolet and in X-rays. It organizes itself around magnetic structures, loops arching between regions of opposite polarity, long streamer belts extending from the equatorial sun, and open field regions at higher latitudes where the field lines splay outward into space rather than curving back to the surface. These open regions are cooler and less dense than the rest of the corona. In extreme ultraviolet images, they appear as dark areas against the corona's bright glow. They are called coronal holes, and through them the sun breathes out. The solar wind begins in the corona. It does not erupt or burst. It streams continuously from the corona outward through the solar system, a flow of electrons and protons and alpha particles that has been moving outward since long before any planet existed to receive it. From the open field regions of coronal holes, the wind leaves fast, 600 to 800 kilometers per second, a speed at which it crosses the distance from the Sun to Earth in 3 days or less. From the equatorial streamer belt, the slow wind emerges at something between 300 and 400 kilometers per second, twisted and structured and carrying embedded fluctuations that interact with the planetary magnetospheres it encounters along the way. Eugene Parker first worked out the mathematics of this outflow in 1958, reasoning from the corona's temperature that no static atmosphere could be in equilibrium. The corona's outer layers, hot enough and diffuse enough, would naturally expand outward, accelerating as they did so. The prediction met considerable resistance. The space between planets was thought at the time to be essentially empty, or filled only with occasional outbursts from solar flares. Parker's continuous structured wind seemed unnecessary. 4 years later, the spacecraft Mariner 2, on its way to Venus, measured the solar wind directly and found that Parker had been right. A continuous stream, structured much as he had calculated, flowing outward past the planets without interruption. The solar wind's effect on each planet depends on whether that planet maintains a magnetic field. Earth does. The geomagnetic field deflects most of the solar wind around the planet, compressing it on the sunlit side and stretching it into a long tail on the night side. The boundary of that deflection is the magnetopause, and within it, the field provides a kind of shelter, not complete, not impenetrable, but sufficient to keep the atmosphere largely intact over billions of years. Mars, which lost its global magnetic field long ago, has been gradually stripped of its upper atmosphere by the solar wind over the same interval. The difference between the two planets, one with a thick atmosphere and liquid water, one with a thin atmosphere and a dry oxidized surface, is partly a consequence of what the solar wind does when nothing deflects it. Where the solar wind is deflected around Earth, some of it enters the polar cusps, regions near the magnetic poles where the field lines funnel down toward the surface rather than deflecting the flow. Particles entering here follow the field lines down into the upper atmosphere, and when they collide with oxygen and nitrogen atoms at altitudes of roughly 60 to 200 miles, those atoms are excited and then relax, releasing light. Green from oxygen at lower altitudes, red from oxygen higher up, blue and violet from nitrogen. The aurora is the solar wind made visible, the sun's outermost breath, traced in color against the dark of the polar night sky. It is a form of light that has been observed, described, and interpreted across every culture that has lived far enough north or south to see it, and what it records is the ongoing negotiation between the sun's outflow and the Earth's field, a negotiation that has been running for as long as both have existed. The solar wind does not only shape the Earth's magnetosphere, it shapes the entire space through which the planets move. Carrying the sun's magnetic field with it as it flows, it creates a vast magnetized bubble, the heliosphere, whose inner region is dominated by the sun's field, and whose boundary is set by the pressure balance between the outflowing solar wind and the incoming flow of interstellar particles. That boundary, the heliopause, lies more than 120 times the distance from Earth to the Sun, far beyond Pluto, far beyond the Kuiper Belt, in a region of space that no human-made object had ever reached until a small spacecraft launched in 1977 crossed it quietly, without ceremony, sometime in the early part of the following century. The heliosphere is not perfectly smooth or uniform. It pulses with the sun's 11-year activity cycle, expands and contracts with variations in solar wind pressure, and is shaped by the interstellar medium pressing in from all sides. But within it, the sun's influence persists, a field, a wind, a presence, all the way to the edge. The corona's temperature, the solar wind's origin, the heliosphere's shape, all of these trace back to the magnetic field. The sun's field is not uniform and static, like a bar magnet. It is generated continuously, renewed and restructured by the differential rotation of the convective envelope and the shearing motion at the tachocline deep inside. The field emerges through the photosphere in localized concentrations, rises into the chromosphere and corona, and organizes the entire outer atmosphere around its topology. Where field lines close back on themselves, loops form and trap hot plasma. Where field lines open to space, the fast wind flows. Where oppositely directed fields are pressed together, reconnection occurs. In large events seen as solar flares or coronal mass ejections, and in the countless tiny events that may, in aggregate, account for the corona's heat. The sun's activity follows an approximately 11-year cycle, measured from one minimum to the next, in which the number of sunspots at the surface and the frequency of energetic events in the atmosphere both rise and fall together. At solar maximum, active regions crowd the photosphere, the corona blazes with magnetically concentrated heat, and the solar wind carries more frequent disturbances outward. At solar minimum, the sun quiets. Fewer sunspots, fewer flares, a simpler and more ordered corona, a slow wind more uniform in structure. The cycle is a surface expression of the deeper dynamo of magnetic field being wound up and released, built and destroyed across a rhythm that has continued for billions of years and will continue for billions more. It is not a perfect clock. Cycles vary in length and intensity, but it is steady enough that every civilization that kept long records eventually noticed it, and every spacecraft that has orbited the sun since the mid-20th century has measured it. The sun's corona does not end at a sharp boundary. There is no surface to it, no wall, no identifiable edge. Moving outward from the transition region, the plasma becomes thinner and hotter, and then thinner and slowly cooler as the solar wind accelerates and expands. The structures, the loops, the streamers, the plumes above the coronal holes become less and less defined with distance, until what remains is a flow of particles and a field still measurably solar in its properties, but no longer organized in any way that has a name. The corona fades into the solar wind, the way a sound fades into silence, not stopping, but becoming something else, and then becoming background, and then becoming the quiet that was always there. At some distance from the sun, the solar wind slows. The termination shock, the boundary where the wind drops from supersonic to subsonic as it piles against the interstellar medium, lies somewhere around 80 to 100 times the distance from the Earth to the sun. Beyond it, in the heliosheath, the decelerated wind churns and presses against the interstellar flow, and then, at the heliopause, the sun's wind effectively ends. The particles beyond it are interstellar, from other stars, from the ancient diffuse gas that fills the spaces between systems, from sources so distant they have no individual names. The heliosphere floats within the interstellar medium the way a bubble floats in open water, its interior shaped by the sun, its exterior shaped by everything outside. One can trace the sun outward from the core, from the dense hot fusing center, through the slow drift of the radiative zone, through the churning of the convective envelope, through the photosphere where light finally escapes, through the chromosphere's thin red shell, through the violent thermal leap of the transition region, through the corona's million-degree glow, and find that at no point does the sun simply stop. It thins, it slows, it cools. It expands into the space around it and carries something of itself, field, particle, wave, across an enormous distance before that something finally falls below the level of the interstellar background. The sun does not have an edge so much as it has a gradient, a slow relinquishment, a place where what is solar becomes indistinguishable from what is not. The chromosphere's red ring lasts only a few heartbeats in an eclipse. The corona blooms around it, white, structured, laced with the curved architecture of magnetic fields, and then the moon moves on, and the photosphere returns, and the ordinary yellow sun resumes. But the corona does not disappear. It is always there above the photosphere, above the chromosphere, always held at its million degrees by whatever process maintains it, always streaming outward into the heliosphere, always connecting the sun to every planet and every particle that moves within its reach. Total darkness hides it. The scattered light of the daytime sky washes it out. At night, the solar wind still arrives, pressed against the magnetopause, threading through the polar cusps, painting the aurora in colors that have names in dozens of languages, and the faint magnetic signature of the heliosphere still stretches across the outer solar system, a presence without a surface, a boundary without a wall. The solar wind that left the corona 3 days ago is already past the moon. The solar wind that left a week ago is somewhere near Venus. The wind that left a month ago is still moving outward, already well past Mars, not yet to the asteroid belt. And the wind that left 11 years ago, at the last solar maximum, when the corona blazed with more activity and the active regions crowded the photosphere, that wind is somewhere near the termination shock, slowing now, pressing outward against the pressure of the interstellar medium, still carrying the sun's field in the spiraling pattern that Parker's mathematics described 60 years ago. All of it continuous, all of it unbroken, a flow that has been moving outward since before the first stone was laid on the first city, since before the first oxygen-breathing animal drew its first breath, since before the oceans were old. The spicules still rise from the chromospheric surface at this moment. 100,000 of them, narrow and quiet from any distance, each one lasting a few minutes before the next. The transition region still holds its steep gradient, 20,000 degrees below, a million above, separated by a distance shorter than the height at which a falcon hunts. The corona still turns slowly around the magnetic structures that define it, its loops glowing in wavelengths no eye can see, its open regions breathing their fast wind into the heliosphere in a continuous, unhurried exhalation. The aurora still forms in the polar sky, not every night, but on nights when the solar wind arrives carrying a disturbance, a fluctuation in the field, and the magnetosphere rings quietly with the energy of it. The light that left the corona during an eclipse 100 years ago has already reached the nearest stars, already passed them, is still moving outward through the interstellar medium with nothing to stop it. The neutrinos that left the core 2 seconds after forming are by now beyond the heliosphere, beyond the nearest stellar systems, still moving at nearly the speed of light through the body of the galaxy, through the body of the cluster, through the long distances between clusters where almost nothing exists. They will not stop.